Until now, we have assumed that fields are scalar, which means that at each point the field has an amplitude that changes in time and the intensity is given by the squared amplitude. However, this is not entirely accurate. What's actually the case is that from Maxwell's equations, it follows that the field consists of an oscillating electric and magnetic field, which are not scalar but vectorial fields. This means that in each point, the amplitude doesn't just oscillate, but it oscillates in a certain direction, and the intensity is given by the squared length of the field vector. The way in which this vector oscillates is what concerns the topic of polarization. Let's start from the vectorial wave equation and see how different types of polarization follow from it. In our previous discussions on diffraction optics, we assumed scalar fields, which obey the scalar wave equation. However, Maxwell's equations involve vectorial electric and magnetic fields, so the wave equation that follows from them is a vectorial wave equation. If we consider propagation through a vacuum, the vectorial wave equation tells us that each component of the electric field satisfies the scalar wave equation. We can write down the plane wave solution, which basically says that each component of the field is a plane wave with the same wave vector k that indicates the wavelength and the direction of propagation, and each field component has a different complex amplitude ax, ay, az, which are contained in the vector a. If we plug this result in the first Maxwell's equation, we see that the amplitude vector and the wave vector have to be perpendicular to each other. What this means is that the oscillating field vector should always be perpendicular to the direction of propagation if the field is propagating in vacuum. Let's say that the field propagates in the z direction. This means that the field should be oscillating in the xy plane and the z component of the field is 0. Therefore, the electric field can be described using only two complex amplitudes ax, ay. If we put these in a vector, we get what we call a Jones vector. Jones vectors are commonly used to describe polarization states. So let's see how we can visualize polarization states corresponding to different Jones vectors. Consider the Jones vector 1, 0. To see what this means physically, recall that the physical real-valued electric field is given by the real part of the complex amplitude multiplied by a time-dependent phase vector of e to the power minus I omega t. In this case, we find that the x component of the field oscillates as cosine omega t, while the y component of the field is 0. In this case, we say that the light is linearly polarized, or more specifically, that it is horizontally polarized. Now let's look at the vector 0, 1. We find the x component is 0, and the y component oscillates as cosine omega t, so the light is still linearly polarized, but now vertically. What happens if we have a Jones vector 1, 1? In this case, both the x component and the y component oscillate as cosine omega t, which means that the light is linearly polarized at an angle of 45 degrees. Now for something more interesting. What if we make one of the components of the Jones vector complex valued, for example 1i? In this case, the field in the x direction is given by the real part of e to the power minus I omega t, and the field in the y direction is given by the real part of I times e to the power minus I omega t. If we rewrite I as e to the power I pi over 2 and write the product as one complex exponential, we find that the field is oscillating as a cosine but with a pi over 2 phase delay compared to the x component. We can also write this as a sine instead of a cosine. Another way to get this result is by noting that in the expression I times e to the power minus I omega t, the complex exponential can be written as cosine plus I times sine. So after multiplying this with I, the real part becomes sine of omega t. If we see what this means for the field vector, we see that at the time t is equal to 0, the x component is 1, and the y component is 0. As the time increases, the x component decreases while the y component becomes larger. When the y component is maximal, the x component is 0. If we complete this reasoning, we find that the electric field vector is rotating in circles, so we call this state of polarization circular polarization. Depending on the direction of the rotation, the light is either right circularly polarized or left circularly polarized. In general, for two arbitrary complex valued ax and ay, the field vector will move in the shape of an ellipse, so the most general state of polarization is elliptical polarization. Linear polarization is an instance of a very flat ellipse, and circular polarization is an instance of a symmetric ellipse. Now that we've seen what kind of polarization states there are, let's see how we can create and manipulate them. Let's start with a simple optical component, the linear polarizer. Let's say that we have a polarizer that only transmits the horizontal component of the field. How do we describe the polarizer mathematically? Mathematically, it sets the y component equal to 0, while the x component is left unchanged. This operation can be described by a matrix 1, 0, 0, 0, which we call the Jones matrix for a horizontal polarizer. If we have a vertical polarizer, the x component is set to 0 and the y component is unchanged, so this is described by the matrix 0, 0, 0, 1. Now suppose we have linearly diagonally polarized light and we want to convert it to circularly polarized light. How do we do this? Mathematically, it's clear that the Jones matrix for this operation is given by 1, 0, 0, I, but how can we achieve this physically? First, let's recall what the Jones vector means physically. It represents the complex amplitudes of the plane wave solutions for the x and y component of the field. We assumed the plane waves are propagating in the c direction, so we can write the complex valued field components as the Jones vector multiplied by a phase vector e to the power I kz minus omega t. Let's ignore the factor e to the power minus I omega t because it's a global phase vector, so it doesn't affect the phase difference between the x and y component, so it doesn't affect the polarization state. We are left with the phase vector e to the power I kz, which is for now also an irrelevant global phase vector, but we'll see in a minute how it can be made relevant. This phase vector tells us that as the field propagates by a distance d, it undergoes a phase shift of e to the power I kd. Intuitively, this can be understood by realizing that if we have a field with wavelength lambda, the phase shift due to propagation can be found by checking how many wavelengths fit in the propagation distance d and saying that each wavelength yields a phase shift of 2 pi. Since the wave number k is defined as 2 pi over lambda, the phase shift can be written as k times d. Now what happens if the field doesn't propagate through vacuum, but through a medium with refractive index n? In that case, the wavelength is reduced by a factor n, so the phase shift is multiplied by a factor n, so the phase shift is given by nkd. Now what happens if we have a material which has different refractive indices for the x component and y component of the field? Such a material is called a birefringent medium, and an example of birefringent media would be crystals such as calcite. In this case, each component is multiplied by a different phase vector, so this operation has to be written as a matrix, namely a diagonal matrix with e to the power I kn xd and e to the power I kn yd on its diagonal. Since global phase vectors are irrelevant to the polarization state, we can factor out a global phase vector of e to the power I kn xd and neglect it. We are left with a complex exponential containing the term ny minus nx, which is referred to as the birefringence of a material. Now we see that we have the correct form for an optical component that transforms linearly polarized light to circularly polarized light. What we need to make sure of now is that this complex exponential is equal to I. Writing I as e to the power pi over 2i plus integer multiples of 2 pi I, we can equate the two exponentials and cancel the i's on both sides. Using the fact that k is equal to 2 pi over lambda, we can divide both sides by 2 pi and multiply both sides by lambda to find that delta nd should be equal to a quarter wavelength plus an integer multiple of the wavelength. Therefore, this optical component is called a quarter wave plate, and in principle it doesn't matter a lot whether it contains an I or a minus I. Similarly, by changing the requirement for delta nd, we can also define a half-wave plate. Let's see what a half-wave plate does and what it might be used for. The matrix for a half-wave plate tells us that the sign of the y component is flipped. So if we draw the vector with the flipped y component, we see that the vector is mirrored in the x-axis. If we rotate the wave plate, the mirror axis is rotated, so the resulting polarization vector is also rotated. And this is what a half-wave plate can be useful for. It can be used to rotate the polarization direction of linearly polarized light without any loss of intensity. We can also define a full wave plate. At first sight, this might seem a bit silly because the Jones matrix indicates that nothing changes to the polarization state. However, we have to remember that a crystal with a certain thickness and a certain birefringence can act as a full wave plate only for a specific set of wavelengths, and for other wavelengths it alters the polarization. So, if you have linearly polarized light of multiple wavelengths, and you let it pass through a full wave plate, and then you filter the light with a linear polarization filter, you have filtered out certain wavelengths, which is what a full wave plate might be useful for. We have seen in the case of a half-wave plate that we may want to rotate it to change its operation on the field. In general, we may want to rotate any optical element, so let's see mathematically how the rotation of an optical element changes its Jones matrix. To do this, let's consider the example of a horizontal polarizer. If we have a polarized field with Jones vector AX, AY, then the polarizer sets the Y component to 0, while the X component passes through unaffected. However, if we rotate the polarizer, this is not true anymore. Rather, we have to decompose the vector in a rotated basis to find the components AX', AY', and set AY' to 0 while leaving AX' unaltered. Since we're now working with two different bases, let's clear up some notation. With J, the physical vector is meant, which means that it refers to the same object regardless of what basis we use to describe it. In the XY basis, J is described by two numbers, AX, AY, which we put in a vector JXY. In the X', Y' basis, the same vector J is described by two different numbers, AX', AY', which we put in a vector JX', Y'. So, even though the two vectors JXY and JX', Y' are not equal, they describe the same physical vector J, but in two different bases. In order to describe how the rotated polarizer acts on the field, we need to figure out how we can find AX', AY' from AX and AY. To do this, let's first see how the basis vectors of the XY basis are related to the basis vectors of the X', Y' basis. If the primed basis is rotated by an angle theta with respect to the unprimed basis, then one can see that the X' basis vector is given by cosine theta times the X basis vector plus sine theta times the Y basis vector. The Y' basis vector is given by minus sine theta times the X basis vector plus cosine theta times the Y basis vector. To find the components AX' and AY', we need to project the vector J onto the primed basis vectors, which we do by taking the dot product. By doing so, we find the relation between AX, AY and AX', AY', and this relation can be written in the form of a matrix multiplication. And so we have found the transformation to go from JXY to JX', Y', and since the transformation matrix is a rotation matrix for an angle of minus theta, we will denote this matrix as R minus theta. This result makes sense intuitively. If you rotate your axes by theta, it is as if you rotate your vector by minus theta. Next, we let the linear polarizer act on the vector, which means we set the AY' component to 0 while leaving AX' unchanged. In other words, we multiply JX', Y' with the Jones matrix M, and the outcome is the transmitted vector JT described in the primed basis. However, we want to describe this entire process in the unprimed basis. So firstly, we substitute JX', Y' with R minus theta JXY, and secondly, we describe the transmitted vector in the unprimed basis by multiplying JTX', Y' by R theta, which is the inverse operation of R minus theta. Combining these expressions gives us that the transmitted vector JT is equal to R theta times M times R minus theta times J. More generally, we found that the Jones matrix for a rotated element is given by R theta M R minus theta. Intuitively, this equation says that you first need to go to a rotated coordinate system by applying R minus theta, then you need to apply M in that rotated coordinate system, and then you have to go back to your original coordinate system using R theta. So far, we have assumed the light is always completely polarized. What we will discuss next is how to describe light that may not be fully polarized. We have stated that light fields have a vectorial nature, which results in light having a polarization. So how does this property manifest itself in experiments? If light is polarized, it means that when using the correct polarization filter, all the light is blocked. For example, if the light is vertically polarized, then a horizontal polarization filter will block all the light. If light is horizontally polarized, then a vertical polarization filter will block all the light. If the light is right circularly polarized, then a left circular polarization filter will block all the light. However, with some types of light, this appears not to be the case. No matter what polarization filter is used, always half of the light is transmitted. It appears as if the light has no polarization. How do I explain this? Recall that we've seen a similar issue before. When discussing the wave nature of light, we saw that in a double-slit experiment a fringe pattern should form. However, For incoherent light, no fringes are formed, as if light doesn't have a wave nature. The way we explained this was by stating that if the phase difference between the fields at the two slits fluctuates rapidly, then the position of the fringe patterns fluctuates rapidly, and since we can only observe time-averaged intensities, the fringes become less visible. The property of light to be able to form interference fringes is called coherence, and it is quantified by the correlation between fields. Similarly, when discussing the vectorial nature of light, we saw that the right polarization filter should block the light completely, but for some types of light, no polarization filter can block the light completely, as if the light has no vectorial nature. This can be explained by noting that the polarization state is determined by the amplitudes of the two field components and the phase difference between them. If these quantities vary rapidly in time, then the polarization state varies rapidly in time, so if we let the light pass through a polarization filter and integrate the intensity over a long time interval, there will always be some transmitted intensity, no matter what polarization filter we use. Looking at the similarities between the theories of coherence and partial polarization, it makes sense that we can describe partially polarized light using the correlation between field components. Let's lay out the mathematical tools that are required to describe partial polarization and compare them to the mathematical tools we use to describe partially coherent fields. To describe a spatially partially coherent field, we compute the correlations between the fields at all pairs of points x1, x2 to define the mutual intensity function. Similarly, to describe a partially polarized field, we compute the correlations between the different components of the field to define the coherency matrix. To describe a spatially partially coherent field, we go from a 1D function to a Hermitian 2D function, or from a 2D function to a Hermitian 4D function. For a partially polarized field, we go from a 2x1 Jones vector to a 2x2 Hermitian coherency matrix, which can be written as the outer product of the field vector. From this, we can see that if we want to apply an operator to a partially polarized field, we need to multiply the coherency matrix from both the left and the right side with the operator. This is analogous to how we need to perform a double integral if we want to apply an operator to the mutual intensity function. Lastly, to find the total intensity of a partially polarized field from its coherency matrix, we need to add its diagonal elements together, which means taking the trace of the coherency matrix. Let's have a look at a few examples for coherency matrices. If we have linearly polarized light, the Jones vector is given by 1, 0, so the coherency matrix, which is given by the outer product, is given by 1, 0, 0, 0. For diagonally polarized light, the Jones vector is 1 over square root 2 times 1, 1, if we want to normalize the total intensity to 1. The coherency matrix is given by a half times 1, 1, 1, 1. For right circularly polarized light, the normalized Jones vector is given by 1 over square root 2 times 1 minus I. So the coherency matrix is given by 1/2 times 1I minus I1. Now what is the coherency matrix for unpolarized light? We cannot write down a Jones vector for unpolarized light because the x and y components aren't fixed in time. Instead, we can observe that for unpolarized light, the correlation between the two components must be 0, and the time-averaged intensity for each component should be the same since unpolarized light shouldn't show any preference for one direction of polarization over another. Therefore, if we normalize the total intensity to be 1, the coherency matrix is given by 1/2 times 1, 0, 0, 1. Now let's look at a different way of describing partially polarized light, which is using Stokes parameters. We've just written down the coherency matrices for unpolarized light, horizontally polarized light, diagonally polarized light, and right circularly polarized light. Note that any coherency matrix with intensity normalized to 1 can be written as the following linear combination with parameters S1, S2, and S3. By varying S1, we can change the values of the diagonal elements while keeping each element real valued and conserving the total intensity. By varying S2, we can vary the real part of the off-diagonal elements. Since the coherency matrix is Hermitian, the real parts of both elements should be the same, so this only gives us 1 degree of freedom. Similarly, the imaginary part should be the same except for a sign change, so that gives us 1 additional degree of freedom, S3. With this decomposition, we can define a Stokes vector which contains the Stokes parameters S1, S2, S3. One can see that the Stokes vector for unpolarized light is given by 1, 0, 0, 0. For horizontally polarized light, it's 1, 1, 0, 0. For diagonally polarized light, it's 1, 0, 1, 0. and for right circularly polarized light it's 1001. So this gives us a way of describing general partially polarized states. But how do we find these parameters in practice? What we can do in practice is letting the light pass through polarization filters, which we describe mathematically by multiplying the coherency matrix from the left and the right side with the Jones matrix and measuring the total intensity, which we can calculate by taking the trace of the coherency matrix. Let's let the light pass through a horizontal polarization filter. We can describe this filter using the Jones matrix 1000 because it lets through horizontally polarized light, which is described by the Jones factor 10, and it blocks vertically polarized light, which is described by the Jones factor 01. If we multiply our general expression for the coherency matrix G with the Jones matrix M from the left and right side and take the trace of the result, we find that the total transmitted intensity is given by 1/2 times 1 plus S1. Similarly, we find that if we let the light pass through a diagonal polarization filter, the transmitted intensity is given by 1/2 times 1 plus S2. And if we let light pass through a right circular polarization filter, the transmitted intensity is given by 1/2 times 1 plus S3. Therefore, in order to find the Stokes parameters experimentally, we need to have these three polarization filters and see how much intensity is transmitted through each filter. From these values, one can straightforwardly compute the Stokes parameters. There exists a nice way to visually represent all polarization states, namely using the Poincare sphere. Let's define an S1 axis, S2 axis, and S3 axis, which we can use to plot any polarization state. Let's consider a fully polarized state with normalized intensity. This state is defined by the amplitudes of each component and their relative phase difference phi. The coherency matrix is calculated by taking the outer product of the Jones factor. By writing the complex exponential in the off-diagonal elements as cosine plus I times sine, we can straightforwardly decompose the coherency matrix in the Stokes parameters S1, S2, S3. If we calculate the length of this three-dimensional vector, we find that it is equal to 1. Therefore, we can find that all fully polarized states lie on a sphere with radius 1. Also recall that for unpolarized light, S1, S2, and S3 are all 0. So in that case, the length of the vector is 0. From this we can infer that the length of the vector is an indication of the degree of polarization, where a length of 1 indicates full polarization and the length of 0 indicates no polarization. In general though, the intensity isn't normalized to 1, but instead it's another degree of freedom as 0, which is the first entry of the Stokes vector. The vector that is plotted in the Poincare sphere is found by taking the last three elements of the Stokes vector and normalizing them by the first element. If one wants to describe the effects of optical components such as polarizers and waveplates on Stokes vectors, one uses so-called Mueller matrices, which consist of 4x4 elements. While it's not required for understanding the topic of polarization and partial polarization, it's interesting to note that there are lots of similarities between the description of polarization states and the description of two-level quantum states, and that the main difference only lies in the terminology that is used. The two-level quantum state may be the polarization of a photon, but in principle it could be any two-level system, such as the spin of an electron or a system with a ground state and an excited state. Light that is fully polarized would in quantum parlance be described as a pure quantum state. A fully polarized state can be described by a Jones factor, which for quantum states would be a wave function that is commonly denoted as a ket vector. Partially polarized light corresponds to a mixed quantum state. The coherency matrix, which in the case of full polarization would be given by the outer product of the Jones factor, is analogous to the density matrix, which in the case of a pure state would be the outer product of a wave function. The four matrices that are used to decompose partially polarized states and which correspond to different polarization states bear close resemblance to the Pauli matrices in quantum mechanics. The Poincare sphere that is used to visually represent different states of polarization is similar to the Bloch sphere that is used to represent different quantum states. To conclude, let's discuss the Fresnel-Arago laws that describe how polarized light interferes. If we have two fields that are mutually coherent and have the same polarization, then they add coherently, so they can form an interference pattern. If the two mutually coherent fields are polarized orthogonally to each other, the total intensity is given by the incoherent sum of the two fields, so they cannot interfere. If we have two fields that are mutually coherent and unpolarized, the total intensity is given by the incoherent sum of two interference patterns. But because the light is unpolarized, the interference pattern for one polarization direction shouldn't look any different from the interference pattern for any other polarization direction. So we're adding twice the same interference pattern together, so we end up with the same interference pattern as if the two fields had parallel polarization. If the two fields are mutually incoherent, then they cannot interfere, no matter their polarization states.